Okay, I know one of the group projects is going to be making an electric generator. So today we're going to be looking at electric generation. We're going to start though with a number of problems. You know, excited to do problems? So here's our first problem. And I'm going to do this problem myself, and then the next problem I'm going to give to you guys. So find the force on the loop. And when you look at this, what you should note is I have current 1 going through the top wire, and then I have some magical system with current 2 going through the loop down below. I say magical system because there's no power supply or anything. It's just showing the currents. You know, you can make this happen. You just have, a power supply and a resistance of some sort. So how is there going to be a force between the loop and the wire on top? What mechanism could make a force there? Magnetic. Good call, since we're in magnetism. But I assume she knows what she's talking about. It is the magnetic force. Because when I have a current going through a wire, it creates a magnetic field. And if I have the wire in the presence of a magnetic field, there's current going through it, there's going to be a force unless, what's the situation that would make it no force? Perpendicular, well, parallel. Yeah, parallel. It's directional, so I went with that, and then I realized, wait, no, parallel. So the first thing we want to do here is say, okay, I need to determine what the magnetic field is produced by one wire at the position of another wire. There's an easy way and a really hard way of doing this. I'm going to go with the easy way. The easy way is I'm going to take this wire here and calculate the magnetic field that it creates here and here. And then I'm going to use some of the other rules I had for problem solving on the other two sides. So let's start with those other rules. I don't think I put in here the rules for problem solving. No, I didn't. But rule number 1 was broken out to like 3 things. So I write 3.
So it's like rule A.
Yeah. Determine if force magnetic is 0. And there were conditions that would do that if current equals 0, if magnetic field is equal 0, or if current, well, the length, I better put it for the wire to be accurate, if current is parallel to the magnetic field. Any one of those gives us a force of 0. If not, then I go to determine magnitude of the force. Force B is equal to ILB sine theta, where theta is the angle between current and length. And then 3, determine direction with right hand rule. RTR for right hand, RTR. RHR for right hand rule, which is just the opposite of His or Her Royal Highness. Okay, so let's look at these. And notice for part A, determine if FB is equal to 0. We can right away say the currents are not 0 in anything. So that is not the case in any situation. I'm going to label these sides, side A, side B, side C, and side D. So the next question, is magnetic field going to be 0 due to the top wire on any of those sides? The magnetic field strength. No answers? Okay, where's the magnetic field? I was going to do that first, but since I started with this other stuff, I didn't do it because I'd still come back. So now that you've asked, I'll do it. Magnetic field. We have wire 1 is the one I'm going to say is making the magnetic field. Of course, the other loop will be making magnetic fields too, but life's a lot easier if I take straight long wire 1 and use that. In fact, without calculus, without using the Biot-Savart law, you can't really calculate the magnetic field created by the loop, because it's a little more complicated. But if I take that top wire, remember the two things we learned in class on Monday. Number one is a right-hand rule for finding the direction of the magnetic field. You take your right hand and you orient your thumb so it's pointing the same direction as the current. So for the top wire, the current is going to your right, so I make my right hand's thumb point to the right. Then I wrap my fingers. Where are all of the loops? Where are all of the loops positioned relative to the top wire? They are all below. So I just put my fingers down below the wire, and my fingers are pointing into the string. So that tells me the direction of the magnetic field at any location below the wire is going to be that's the direction of the magnetic field for all places on this. There, I put a lowercase b so I can use capital B for the magnetic field. So the magnetic field, we have its direction now. And then we have the equation for the strength, which we found by using Ampere's law. According to, and of course, we always say Ampere's law, but especially because certain students giving me grief for mispronouncing French words, trying to say it right. I'm sorry, I keep looking at it. Okay, the magnetic field strength is equal to mu naught I over 2 pi r is what we found from applying Ampere's law to a long infinite wire. So we have this here is going to be RA, and going from here to here will be RC, and I probably shouldn't have used the same colors I used for magnetic field now, should I? So RA and RC are easily defined. Now for sides B and D, the radius is changing, so the magnetic field strength is changing as you move along those sides. That's a little bit disconcerting, isn't it? But now we can come back to, right, that answers your question about the magnetic field, right? So now we can go back to and answer more easily, is the magnetic field zero on any of the sides? No. Okay. Then finally, is the length parallel to the magnetic field on any side? No. So we got rid of all of the zeros. And that's a little more troubling because remember we said the sides are going to be hard because we have changing magnetic field strength. Now if you're in the calculus class, you can do that. We're not in the calculus-based class here, are we? There's got to be another answer to make it so we can do this. So, what was that?
There's nothing major.
Nothing major. I'm going to jump down to step 3. 2 and 3, it doesn't matter which one you do first. I'm going to jump down to step 3 and do that next because that will help us take care of B and D. So determine the direction with the right-hand rule. So the direction for the force, remember the equation for the force was force equals IL cross B. So if I look at side B, my current in side B is going like this, which means that I'm going to use that for the direction of L. So I take my right hand, I put my index finger in the direction of that current, so my current's going up, index finger's up. Then I need to orient my hand so my middle finger's point in the direction of which vector. Okay, not supposed to ask questions. Which vector should my middle finger point parallel to? No, that was index. B, because it's the second item. The first item in cross product is always your index finger, the second item is your middle finger. So I now orient my hand like this, and my thumb is pointing the direction of the force. So the force is going like that. Now I look at side D. I was going to call on Lydia, but she actually wasn't here on Monday. That would be unfair. Michael, lead us in applying the right-hand rule on side D here, where the current is going down.
Okay, so current's going down, that means
Index finger?
then perpendicular.
Okay, so I need my middle finger to go the direction of the magnetic field, which is into the screen.
Oh, sorry.
So go like
And once again, a reminder, when you're doing a test, you can just move the paper around instead of having to contort yourself. Yeah, you're good, Ryan. You got it.
For some reason, I was looking at the bottom one and it looked like a dot.
And so you end up with your thumb pointing, here, this is the easy way, like this. Now, force B and force D are pointing in opposite directions. They're symmetrical in terms of they have the same current, the same positions. So those forces are going to have to be equal to each other. Based on symmetry, they have to be. But they're in opposite directions. So if they're the same magnitude in opposite directions, what do they add up to? 0. So we have force B plus force D add up to 0 because their magnitudes are the same and their directions are opposite. Now, we're not done, but what we've taken care of is the two hard ones. Now we have the two easier ones. So let's go to Maddie. What direction is the magnetic force on wire A, the top wire, going to be? Yeah, at least with using the right hand. I'm calling out people because I want to make sure people know how to apply the right hand rule, not just me doing it all the time. So which should your index finger point parallel to?
Are you talking about all of them?
Well, I was asking Maddie, but other people can help.
I don't even help, right?
The index finger should point with the current.
With the current, right. So your index finger is pointing with the current. And then you orient your hand so you can point your middle fingers in which direction?
Into the screen.
Which is
Magnetic.
the magnetic field. So I orient my hand so my index finger is with the current, my middle finger the magnetic field, and that force is then down. So the force in the top one is down. And finally, Mira, the bottom wire. Good. What direction should your index finger be and your middle finger? Okay.
So that means you're supposed to go up.
Index finger is parallel to the current, so going that way. Middle finger parallel to magnetic field, thumb points up. Now, if you look at this, you're like, well, that was probably unsurprising because all of the forces are pointing toward the center. We had force D and force B, I said, added up to 0. Does that mean force A and force C add up to 0? C. What say ye?
Well, they have the same current in distance. So yeah, sure.
No, because they are the same current, but the magnetic field is different on the bottom than in the top. On the sides, we have the same magnetic field at the same elevation, so each piece would cancel. But the top is a stronger magnetic field, the bottom is a weaker magnetic field, so we're not going to have them add up to 0. So we actually have to do some math.
Because of elevation?
Well, because of the distance, the RA versus the RC. And so now I have to calculate what the magnitude, force A, so the magnitude is going to be my current in wire 2 times the length of A, which I'll just put LA here, times the magnetic field. The magnetic field we calculated right here, and that's due to current 1. So there's equation-wise what the force is between the long infinite wire and the finite piece of wire. Notice it's proportional to current 1 times current 2. And it's proportional to the length of the wire. In many cases, we actually just calculate the force per length, so we divide out the length of the wire, and we'd have force over L is equal to mu naught I1, I2 over 2 pi R. So that's the magnitude of force A. How would I calculate the magnitude of force B?
Same thing, we just changed the.
Yeah, it's still the same length of wire, so it's still LA. I mean, I could call it LC, but LC equals LA. Times I1 times I2 over 2 pi RC. Therefore, the sum of the force vectors is equal to, and looking at which one's up, FC was up. So I'm going to put FC minus, and that should have been. Now, RC is bigger, so it turns out it's down. It's going to give me a negative value up. I'm not going to actually put the numbers in, mostly because I'm at the very bottom of my page here. At least I think I'm at the very bottom of the page. I tried, yeah. But that's how we can calculate the net force on that loop. So important outcomes here are a wire carrying current in the presence of another wire carrying current is going to make a force. That's actually a really important outcome. The definition of what an ampere is coming up in 2 slides, and it's based on this calculation. So I'm not going to write it now when it's going to come in 2 slides. Instead, I'm going to give you a problem to work in your tables. And why don't we have Michael and Lydia work together there. So here in household wiring, 2 long parallel wires are separated and surrounded by an insulator. The wires are a distance d apart and carry currents of magnitude I in opposite directions. So in this picture, the top is current coming toward you, and the bottom is current going away from you. And then it says find the magnitude of the magnetic field at this point. Now, this is not the force between wires, it's finding the magnitude of the magnetic field.
Why is it greater than greater than?
Greater than means much, much greater than. For now, just find your answer without worrying about that, and then I'll explain.
Okay.
Define theta so we can all use theta the same. The wires are the things on the left. The wires are this current going away from you and this current coming toward you. The current is the dot. So the top is coming toward the bottom. This is the current. This is the current. Well, this one here you find the magnetic field, not the force. So for the magnetic field, you're using the rule where you point your thumb in the direction of the current and then wrap your fingers both directions.
So you point your things and you put your thumb in the direction of the current?
Make sure your thumb is sticking out. When you use the right hand rules, you always need to have your thumb sticking out. So it's perpendicular to your index finger or the plane made in curl. So your thumb, like for the top one, your thumb is coming out of the screen, right? And then what direction your finger is pointing at?
Oh, wait.
Or point
So
P.
wait, your thumb has to be the little dot that's pointing out.
It's the current.
Oh, okay, so it's pointing out and then wrap with you.
You wrap your fingers and you say, what direction my finger is pointing at point P.
So you mean like opposite of what this shows? See, I'm confused.
No, it's exactly what this shows.
Yeah, so this is way, this direction?
Well,
So that's not a
Yeah.
if I take my thumb and put it like this,
Yes.
I need to see what it's going to be over here. So I need to orient my hand so I can have my fingers on that side. What direction my finger's pointing at this location. It's not exactly up.
It's right.
It's mostly up. So you're going to have,
See, how do we define that direction? Because yeah, it's like not up, but not right.
because it's got to be perpendicular to that black line.
You think that's a little entrance?
Well, you're trying to find the net
Yeah, I did. I'm gonna put myself
I
out.
think it's this
I'll ask you. And then you'll take care of it. No, I'll come back.
Yeah, this one.
I only want the one.
So, right hand roll for which one?
Yeah, that was the root part.
This is the direction.
That's if you only have current. So the direction of the magnet you No, it wasn't. It was. But when you try to find the force, the direction of the force, that's what we did here. You have to put your direction of current.
Oh, it has forces.
And then
This is the other distance.
he goes, you weren't.
I think my brother.
Exactly. Right, so we just have current. In the white dress, and then the force is. Oh, yeah. So the force is going this way.
Yeah, we'll maybe throw those guys off. You guys have nice ways. And then you guys that's fine, I'll find some.
This one, force two.
Would it be like this?
I don't really know what to do now.
Okay. You have the magnet field, it's pointing that way, you run this one. And so, what's the strength of the magnet field?
I don't know what the number.
Well, you have this, here's D, so this distance here is 1/2 D. Okay, this distance here is altered that way. You got that equation.
Oh, so, okay, so it is. I don't know if it's true.
You said 0, it's supposed to have such a 0. Is the permeability of free space, it's telling you how magnetized it is. So, vacuum is.
And then,
Because that's.
I mean, the direction is just well, you have to have a distance from here to here, the distance from the wire to here to that works. And so, what happens is the magnitude and the find the total
sign or find the.
Okay.
What is the number of that permeability?
Using a trick.
4,
Another beginning
5,
way to do this.
Yeah.
times 10 to the
So you
negative
just say it's where.
You have to do every one.
centimeters per acre.
4 pi,
It's just
or like 10 to the.
You're gonna find the magnitude of this. Then you have another one do this, that's going in a different direction. They'll have the same magnitude because they're same choice. And then you have to add those two vectors as those two magnetic fields as vectors.
Let's just do the force one. Force one, what is force one? Yeah, but I don't. And it doesn't give us the negative wire, so that, we just say like.
We're assuming.
Okay, so I'll just put.
There's no, you're not calculating the force. You're calculating magnetic field.
Oh, right.
Yeah, that's why we usually put force per light, because we usually like it per light.
Okay, so this is the magnetic field. The wire one. And. And it'll still be the same radius, right? So the only difference is where you can the direction. So this one would be negative.
Vector in both wires.
What direction will
We have to solve it.
This is why I say you can not take paper. This one you don't.
We see that copy, we don't do
That's right, right? I mean, if they were just assuming that. So then another one. So we have these two.
So it's.
How do we end?
Can you see that?
But it also gives us one current.
Perfect.
But then it would be.
No.
That's the. So.
Yeah.
It's like.
Maybe the distance that we're
Like
looking
you had
at.
a, like, oh wait.
I think we're taking the magnetic force of wire 1 in wire 2, and then finding the difference.
Okay, we've worked on this for a while. I think it's
Both of them are different from point
Yes.
Well, we have a-
I think we'll make it this year.
the directions.
and then so let's
Let me work it out. Okay, I'm gonna work it out now. I think everybody's had some fun working with this. Hopefully you've clarified some thoughts in your mind as we did this. Goes back to some of the basic things we've learned in first semester, but obviously applying the magnetic field things. So I showed you how we used the right-hand rule to find the direction of the magnetic field due to the top wire, which I called BA here. Now, BA is going to have a magnitude of mu watt times I over 2 pi. And to make my life easy, I'm going to call this side of the triangle C for now. C is the separation from my current to my point. Remember, the equation that we had was mu naught I over 2 pi r, and r was the distance from the wire to where we find the magnetic field. Since r is already taken in this problem to mean something else, I'm using C for that variable. So that's the magnetic field due to the top wire. Now for the bottom wire, using the right-hand rule, again, pointing my thumb this time into the screen, and orienting my hand so my fingers are at the point P, I see that it's going down and to the right. And once again, because my horizontal, I'm going to just put in green, that's perpendiculars, and then the black line is perpendicular to the B, then the angle between the perpendicular and B has to be that same theta. And the magnitude, because it's the same current and the same distance, is the same. But now I have to add those as vectors, right? Magnetic fields are vectors, not scalars. So my magnetic field, A, is equal to BA times sine theta in the x direction. Before I can actually write that, I have to define what x and y are. Plus BA cosine theta in the y direction. And similarly, magnetic field due to the bottom wire is equal to BB sine theta in the x direction minus BB cosine theta in the y direction. Now, just to make sure we're really clear, why are both of the x components positive? They're both going toward the right. Why are the y components one positive, one negative? One's going up, one's going down. Why is the x component, why does it have sine theta for x?
Because of the orientation of the triangle.
Yeah, because the orientation of the triangle. Remember, first semester I made a big deal. You always have to pay attention to which angle you have. You know, probably 80, 90% of the time it's going to be the x component is corresponding with cosine theta, but it depends on your triangle. Now, BA and BB have the same magnitudes. So I'm going to go ahead and replace my BBs with BAs in this equation because they have the same magnitude. That is, these two are equal to each other. And so if I add these up, magnetic field total is equal to 2 BA sine theta in the x direction plus 0 in the y direction. Now I'm pretty much done, except for I don't have it in terms of what R and D are. So let's figure out what sine theta is. So if I look at this picture, sine theta is the opposite side, which is d over 2. Right, this is d over 2, divided by the hypotenuse, which is c. So I can put in here equals 2 times mu naught I times d over 2c divided by 2 pi c. My 2's cancel, and I can rearrange to mu naught I d over pi c squared. Now I need to put in what c is. How do I calculate that side c?
Isn't there supposed to be an extra 2?
I can't, oh, yes, I canceled 2 2's and canceled the third one as well. You are right. There were 3 2's. Okay, how do I find that length c? Pythagorean theorem. So c is equal to the square root of r squared plus d over 2 quantity squared. So since this is c squared, that's going to be r squared plus d over 2 quantity squared. So now writing my answer, I put a square twice. Sometimes, okay, I erase the square, nobody knows. I should have had it like that. There were 2 mistakes in the way I wrote this. There. That's correct. So that is a perfectly correct answer. And so people were asking, why does it have R greater than D? That's just a mathematical thing. That's saying we're going to take the limit where R is much, much bigger than D. So if I have R squared plus D squared over 4, if R is much, much bigger than D, that's like, let's say R is 1,000,000 and D is 1. 1,000,000 squared compared to 1 squared, that 1 is insignificant. That's the point of R much, much greater than D. We're just going to drop the D squared over 4 from the denominator because it's insignificant in this case. So I'm going to put approximately equal just because I did make an approximation here for R much, much greater than D. Mu naught I d over 2 pi r squared. Now notice the d on top did not disappear because it wasn't being added to an r. I can't do that. It's only where I had the r squared plus the d squared over 4 where they're added that I was able to make that disappear. So that's the answer that we were looking for. So if there's a magnetic field out there, that means we can have some interaction. The second part of the question says, well, let's just put in numbers to see how big this is. So if we have 5 amps, 5 amps is a very reasonable current. Your household circuits should go up to 15 amps. Distance is 5 millimeters. That's the separation between the 2 wires. 5 millimeters, about that far. That's kind of reasonable for a power cord. And then we're 1 meter away. So if we put in those numbers, And so I'm just going to do the magnitude. 4 pi times 10 to the minus 7 is like Tesla. I don't remember its units. I really don't. They're on the next slide. Times my current of 5 amps times the separation of 0.005 meters divided by 2 pi times 1 meter squared. I should drop all the units because I don't know the unit of my constant. And so 5 times 0.005 is 2.5 times 10 to the minus 3. 4 pi and 2 pi gives me 2 times 10 to the minus 7. Actually, it's easier to do it this way. 2 times 5 is 10. 10 times 0.005 is 0.05. So that's 0.05 Teslas. How does that compare to the Earth's magnetic field strength? Really? Wait, did I do that right? No. No, I did not do that right. Whew. I was like, that's really big. I forgot the times 10 to the minus 7. So I have 1 times 10 to the minus 6 times 10 times 10 5 times 10 to the minus 3. 5 times 1 is 5 times 10 to the minus 10 Tesla. More like it. It's a very weak magnetic field. If things are closer, though, it makes a difference. And so if you have wires in your house, like let's say you have electric wires, because we all do, and then you have a network cable for communicating on the computer. If those are close to each other, then your electric wires are going to actually have changing magnetic fields that are going to induce currents on your wires for your internet. That's a problem. So you don't want to have your internet wires close to your electric wire. If they're farther away where the magnetic field is so small like this, it's not such a big deal. The reason the wires have the two incoming outgoing currents close together is so that it comes to very small amounts like this. If you had just positive current going this direction and nothing coming back beside it, you'd have much bigger magnetic fields, much more interference. A final thing, if you're running wire in your house, when I moved here to Lincoln, I put internet cabling throughout my house because it didn't have any. You want to make sure that you have where your internet cable crosses your power lines, they're perpendicular. Why perpendicular? Because then the magnetic fields aren't going to induce any currents. If you have them parallel, they'll induce currents. If they're perpendicular, they won't. So those are just fundamental rules for doing electrical wiring in a house to avoid having problems. And of course, I would have said telephone cabling, but who uses a telephone in their house anymore? Yeah, no. You guys won't. Your parents probably still do, right? Some yes, some no. I abandoned the house telephone more than a decade ago. No, not more than a decade ago, because I didn't get a cell phone until 7 years ago. I abandoned it about the year after I got a cell phone. All right. Any questions about how we did those two problems? Those two problems are fundamental skills that you're going to need to know come next test time. Wes?
How did you get the directions for the magnetic fields again?
I got the directions. Okay, we know that the magnetic fields are doing circles, right? So that means it's always going to be perpendicular to my radius line. So my radius lines were those bold black lines. So it had to be perpendicular to that line. And then I used my right-hand rule to determine which direction perpendicular to it was. All right, so there's the units I couldn't remember. Newtons per ampere squared, apparently. Mu watt is a fundamental constant that's defined as exactly 4 pi times 10 to the minus 2 newtons per ampere squared. It's actually defined that way because of this statement down below. The ampere is the fundamental unit. Remember I told you before, the coulomb is not considered a fundamental unit. It's a derived unit from the ampere. The ampere is the fundamental unit, and the ampere is defined as the current going through each wire separated by 1 meter. So I have 2 wires separated by 1 meter, and I'm going to make my currents go the same direction. If they have the same current, then it's going to produce a force per unit length of 2 times newtons per meter. That's how we define the current. So if we look at the force, this is going to be just like what we did in the first problem. Now, what direction will the force be on these wires? Is it going to be attractive or repulsive? It's a two-stepper. What do you say? Okay, so we have an answer of attractive, which I think is right, but it's a two-stepper to determine. First, you need to determine the direction of the magnetic field at one wire due to the other. So let's say, for instance, that I'm going to take the right wire as my wire 1. So the magnetic field at wire 2 due to wire 1, right hand parallel to the current, or thumb parallel to current, fingers wrapped so they're going in. So that's the direction of the magnetic field at wire 2 due to wire 1. It's going to have a magnitude of mu naught I1 over 2 pi, and I'll call this separation here D. Nice job on that line. So that's the strength of the magnetic field, and this direction is shown, I found, with the right-hand rule. Then step 2, force is equal to I2L cross B 1. So then I'll put my index finger parallel to L2, which is up. My thumb going in. It's not attractive, is it? It's repulsive. So using the right-hand rule, we found the force of wire 1 on wire 2. And once again, the way you label things is kind of up to you. There's no rule specific that I know of. It's going to be out, so it's repulsive. The parallels are the same direct. If the currents are the same direction, it's repulsive. Opposite direction, attractive. It's like the force between charges. Opposites attract, likes repel. Do you have questions, sir?
When you put your index finger towards the current, parallel to the current, and your middle finger to the method,
Apparently not. You're right. I did that wrong somehow. It's good to have Sarah here. How did I do that wrong? I think the problem is I did here and then wrote the same direction here. Okay, so let's make sure we all do this the same. Index finger needs to be in the direction of L2, which is up. Middle finger in. Okay, so parallels attract in this case. Thank you. So now if I put my numbers in to find the magnitude of the force, or not my numbers in, but my symbols, that's equal to I2 L2 mu naught I1 over 2 pi d is the force magnitude. So the force per length is equal to mu naught I1 I2 over 2 pi d. And now we can see by that definition I ran out of space. That will give us, on top we have 4 pi times 10 to the 7 divided by 2 pi gives us 2 times 10 to the minus 7 newtons per meter. That's how we define the current. So in theory, anywhere on Earth, you can get 2 wires, 2 very long wires, and put a current through them, measure the force between them. When it gets to be 2 times 10 to the minus 7 newtons per meter, you know that your current is 1 amp. That's why we use it as a definition, because it's reproducible anywhere on Earth. Goodness. This was the topic we were supposed to do. All of that was review. It's good to be staying with the program. We are out of time. So have a great day, and I actually won't assign any new homework. I'll just take the homework that's due tonight and move it to Friday because we didn't cover anything new. The expert TA, right. What was that?
Expert TA is not due tonight?
I'm going to move the one that's due tonight just to Friday, not make a new one. Still keep up with the reading quizzes. The reading quizzes are going ahead probably by a week
We're
now.
like in the next chapter already.
Yeah, we're way ahead.
Wait, how far is it?
We're at the end of chapter 23.
What is the topic?
The souls?
We just finished doing like
Well, I will.
transformative stuff.
Yeah, transform.
I don't want you to move out of magnetism. If it goes to something beyond I'll look at them, but don't worry about going beyond magnetism.
Right now, we just finished doing transformation of.
Yeah.
Yes, ma'am.
We just finished the one that was assigned for today through Friday, and we covered RLC series AC circuits. That's the last section.
Yeah, so I'll postpone that too, because we need to finish this before we start the circuits.
Wait, so then,